So I'm delighted to introduce to you our very distinguished panel. We have three people on the panel, Professor Gul Agha, Professor Srikala Bajwa, and Professor Shashi Shekhar. Gul Agha is a professor of computer science and electrical and computer engineering at UIUC. He is the co-founder of Embedded Technologies, a fellow of the IEEE, has served as editor-in-chief of a number of journals, including IEEE Concurrency, Parallel Distributed Mobile Computing, ACM Computing Surveys, IEEE Computing Now. And he has pioneered novel coordination languages, methods for software testing, statistical methods for verification, and algorithms for sensor networks. And the key thing here that I guess is central to the sensor area, besides the sensor networks, is he's developed a long-term autonomic structural health monitoring system for civil infrastructure. And so basically, this is using networks of wireless smart sensors to figure out what's going on in infrastructure, such as railroad and bridges. Professor Bajwa is professor and chair of the Department of Agriculture and Biosystems Engineering at North Dakota State University in Fargo. She'd previously been at the University of Arkansas. She is an expert in agricultural remote sensing and precision agriculture, and has worked on the application of multisensory data collected with aerial systems for monitoring field crops and livestock, and applying, in effect, the results of what one gets from these sensors to the problem of precision agriculture. She's a member of the ASABE Global Engagement Task Force, exploring engineering solutions to the global challenges of food, water, and energy security. Professor Shekhar is the McKnight Distinguished University Professor at the University of Minnesota. He's an alumnus of UC Berkeley and a leading scholar of geographical information systems and spatial computing. He is on the board of the Computing Research Association, is co-editor-in-chief of the Geoinformatica Journal. He has served on many National Academies committees, on the CRA's Computing Community Consortium Council, on the UCGIS board, and has won a number of awards, including the IEEE Computer Society Technical Achievement Award, the UCGIS Education Award. He's an IEEE fellow, a AAAS fellow, and has written a popular textbook on spatial databases. So we're fortunate to have three such distinguished panelists, and I'd like to ask Professor Gul Agha to begin.
So my topic is on infrastructure monitoring, and been working for the last 15 years on this project with civil engineers. So let's start with this story. Back in 1967, on the Ohio River, there was a Silver Bridge collapse, and then this killed 46 people. So Congress mandated, in the aftermath of this disaster, biennial visual inspections for every bridge, which helped identify a lot of bridges that had to be repaired or demolished. 1 month earlier, there was another bridge completed in Minneapolis. That was the I-35 bridge, which collapsed in 2007. So bridges continue to fail despite regular inspections. In fact, all recent failures have happened where there have been visual inspections. So visual inspections clearly aren't sufficient or adequate. There are many causes of failure. There are design faults, lack of maintenance, but moreover, the infrastructure is aging. We have over $20 trillion worth of civil infrastructure in the US alone. A lot of these bridges are more than 50 years old. Bridges are accounting for half the cost of highways, by the way. But also, buildings and other infrastructure. The visual inspections themselves are not reliable. They're estimated to be about 50% false negative rates. Just as an example, here's an example of Chicago's bridge at 15th and Halsted. It's the state of the bridge. You can see how they're looking. Here's a bridge over the Metra, which is structurally deficient. It's not an exception. Basically, we have bridges have been rated as C by the American Society of Civil Engineers. There are over 70,000 structurally deficient bridges in the US alone. So the question is how to then target maintenance and improve safety of these bridges, which require tens of billions of dollars of investment, hundreds of billions, but you have to sort of rationalize this investment over the years and prioritize and figure out what really needs to be done. Moreover, there are impacts. So there's just not a regular question of sort of decay, but trucks and so on hit bridges quite often, and sometimes it's not even reported. And even when it's reported, you don't know what the impact is unless somebody goes out there and visually inspects, which is a costly process. So what we'd like to do, what we've been doing in the Illinois Structural Health Monitoring Project is to develop software and hardware to develop a system for monitoring the infrastructure. So this is in collaboration with Professor Bill Spencer, a colleague of mine in civil engineering, and Kirill Mechtoff, a postdoc, and dozens of graduate students have worked on this with support initially from DARPA and then from NSF. So what we're doing is trying to make these bridges smart. So essentially take hundreds of sensors, put them on a bridge, and monitor continuously every element of the bridge. We've executed a number of deployments on a rock arsenal bridge over the Mississippi River, not too far from here, the Little Calumet Bridge, Canadian National Railroad. The longest and largest deployment was the Jindo Bridge in South Korea, which employed 700 sensors, which is over several years with 700 sensor channels, about 100 nodes. Got lots of publicity in The Economist and so on. So essentially what we want to do is to turn the bridge into a smart structure. So in this case, the bridge itself can report, for example, if there's an impact on the bridge or if there are structural issues. In fact, we got lucky from the research point of view. A typhoon went by on this bridge during our deployment over the years, and we were able to record the response of every single element and wind speeds at the bridge. So the technology involves, of course, I don't have time to get into the details of the technology, but the technology involves many components. There's the sensors themselves, which are customizable, and they are getting strain and vibration, which is high frequency sensing. And then there's a sensing system, so you get these hundreds of sensors and high fidelity data out of these sensors. So these sensors can measure things, and then we can create higher level information, which is useful for the engineers. So we have developed a number of platforms, a whole series of sensors to achieve this: 3D acceleration, humidity, light, high sensitivity accelerometers, data acquisition boards, strain sensors, pressure sensors, things of this sort. We pushed this technology out into trying to get it into the marketplace by creating a startup out of the University of Illinois called Embedder Technologies. We won the Chicago Innovation Exchange Award competition from hundreds of startups. And so that's developing. So besides the hardware, there's the software. So there's a tool suite with hundreds of thousands of lines of code doing reliable communication, and has to be energy sensitive. We have to do very careful energy management. These are wireless sensors. Many bridges don't have power lines on them. For example, railroad bridges that are out in the field. Even if there's power, that's very expensive to wire. Network data aggregation, correlation function estimations, test suites, essentially a whole bunch of software. The software, the key idea behind the software brings our expertise in computer science and distributed computing. You have masses of data, and you cannot possibly take all this data and push it at high frequency sensings that you're doing at hundreds of hertz to a centralized station. So it's like, for example, the retina gets more information from the brain to suppress. If you look at even the eye of a bumblebee, it sends 10 times as much information from brain to the retina as from the retina to the brain, because the brain doesn't want to be flooded. Distributed computing is how nature handles masses of data. So if you want any kind of real-time response, you have to bring distributed computing. That's what we bring through this sort of actor-oriented architecture, which is something that I've worked on for the last 25 years. So this provides mobility, security, and efficiency in the distributed processing. So rather than centralize the data, which has been done, but if 10 minutes of data or something takes 8 hours to get out, and then your batteries are dead, we're using radio and wireless channels. We use decentralized and hierarchical processing. So that's a key idea. And one of the things we do is, an example is railroad bridge monitoring. Here we have displacement sensors and strain sensors, and you can sort of see this video here of as a train goes by, we can calibrate and strategically place smart sensors that tells you exactly what the force is on the tracks and what the state of the tracks is. Not only what the state of the tracks is, but what the load on each car is. We can tell exactly how loaded each of the cars is. And this gives you a fine-grained analysis, and you can sort of continuously monitor the state of the track, the state of the bridge, the state of the structure. So this kind of analysis, not just the main mode, but also the secondary modes of the structure, which tell you the state, and they're very important in the analysis. What makes this technology feasible now to move into the field is the cost factor. So some signature bridges have been instrumented, and the cost of deployment has been anything from $10,000 to $25,000 per channel because of the cost of wiring and maintenance and high-fidelity sensors. We are able to get this with digitization and wireless sensors down to about $200 per channel. So at this point, it becomes feasible to start to put thousands of bridges under continuous monitoring. So this basically brings me to the conclusion of the talk. The vision then is these smart structures. We can monitor in case of hurricanes, in case of collisions, trucks hitting. The image I showed you of the truck hitting the bridge, we can tell in real time what the state of the bridge is and what the damage is, and localize it. It can help monitor the traffic. We can tell the loads on the bridge. We can tell how many cars are passing through on all the highway passes. Of course, there are other applications in case of the environment and manufacturing and processing elements, which all in intelligent manufacturing. You have to stop the factory to retool. So if you can plan this out and know what the state of the components is, and vibration provides a signature. You can think of it analogously to, like visual inspections are like you go to a doctor and they lack a stethoscope. And now here you have a continuous stethoscope implanted into your infrastructure to monitor continuously, to get data and huge amounts of data that can then be analyzed and rationalize the process of repairs and process of maintenance. Even process of inspections can be rationalized by picking and choosing where the inspections should start and how they should happen. So this, and of course, eventually we'll have monitoring of buildings as well as structures, because they get wind and other shear forces that act on them. And so this can help in plan for emergency responses in cases of things like hurricanes and earthquakes and so on. You can get real-time response out of the system. So that's basically the idea, to increase the diagnostic tools to create smart cities by making the infrastructure itself smart rather than passive and something to be observed. And I'll stop here.
Good afternoon. I'm Shrikala Bajwa, and I'm going to change the topic a little bit. My presentation is also about the application of big data, but from transportation to agriculture. I was asked by Aaron to talk about in the last 2 years, we have been working with unmanned aerial system applications in agriculture, and to talk about some of the sensors and the data we dealt with. So our project has 3 major points: partnership, research, and education. So I thought I'll start with the listing all the partners here. We worked with a bunch of researchers, academicians from different fields of primarily agriculture, but outside of agriculture too, because one or two of us don't have all the expertise that is needed for this kind of work. Also, we had a lot of partners from outside of the university, actually from many different avenues. We worked with the citizens from many different avenues. One of my critical partners is sitting there, Terry Sanders from the Grand Forks Economic Development Corporation. We had several funding partners, industries, government, and commodity boards, and also non-funding partners, farmers, agriculture consultants, utility companies, Northern Plains Unmanned Aerial System Test Site, many, I can't list all the people here, but many people there. So our research was, or our project was to develop and evaluate agronomic applications of unmanned aerial system in both the crop and agronomic application in crop production and also livestock applications. So some of the things we are looking at, many of the speakers here earlier today talked about the lack of data analytics. It's the same in agriculture. There is big set of data coming from multiple sources, but there is a lack of analytics. So we were looking at some of the specific application, plant stand count. One of the farmers I work with, he farms 30,000 acres, and he said once that plant comes out, you plant the seed and it germinates, he puts $80 per acre. That's around $2.4 million for his 30,000 acre farm. So he makes a decision on what to do with that $2.4 million, depending on how many plants have germinated. So one of the things we looked at is within 1 week of planting, counting the plants, how many plants have germinated. In-season crop fertility management. Again, we have some soil scientists here who are working in this field, but in most crops, nitrogen is a major fertilizer input. So how can we say how much fertilizer is needed and where it needs to be applied? Weed identification and management, weed species, what weeds are there, and also another aspect we are looking into is herbicide resistance, especially with increase in glyphosate, which is a herbicide application in agriculture. There is a lot of resistance we are seeing. And also herbicide injury. You apply one chemical to corn, it drift and fall on another crop, and what degree of injury is there. Crop disease monitoring. Yield correlation, can you look at your image or field and say that what yield you are expecting later in the season? So that is also part of how do you incorporate images you get from unmanned aerial system into some of the yield prediction models. Livestock inventory, movement, location. In 2 years back, we had a major snowstorm in October in western part of North Dakota. Many cows died. A cow could cost $2,500 or $3,000. So it's a lot of money for a rancher when they don't know where that cow is and it dies. So those are some of the applications we are looking into. And also for our partners, a farmer is not going to adopt something, a new technology, unless you can show that this is profitable. So what is the business model? What is the economic benefit to the end user, who is the farmer, and also the companies who are coming to partner with us, as an unmanned aerial system company or a precision ag company, what sort of business model makes sense to them? And we are part of extension education, so another interest is educating the people and also providing data to the cooperating farmers. So I want to talk a little bit about a large UAS project we had. This is anything below 55 pound is small UAS. This is a 1,200 pound unmanned aerial system from the airplane is called Hermes 450, and we were flying it. Our original plan was to fly it twice a month during May, June, July, and August. We were going to collect color and infrared image, or visible and infrared image, at 3 different altitudes, 4,000, 6,000, and 8,000. It corresponds to 3 different spatial resolution of the data, 4 centimeter, 6 centimeter, and 8 centimeter. And we were also, for selected field, we were also going to fly small UAS. Choosing a number of different sensors depending on the application we were interested in. And we were also collecting ground data at the same time. So one of the things I want to show is that our large UAS, it can cover 25,000 acres in 1 hour compared to the small UAS. I'm using a Trimble UX5 here as an example. It covers at 400 feet elevation, it covers 500 acres in an hour at 2-inch resolution versus, 2-inch resolution versus roughly 2, both are roughly 2-inch resolution. So our this 2016 research with this large UAS, it was done in North Dakota. We had a sample or an area of study which was around 102,000 acres, or a 40-mile by 4-mile corridor. It spanned 2 different counties and around 500 landowners in that area, and we have no way of knowing how many farmers. Many times landowners are not same as the farmers. And since this session is about the sensors, there are a bunch of sensors we used. Actually, any UAS you buy, it comes with a selection of sensors in it. Or you can also buy sensors from outside of that company and use it with this with the UAS. But we had anywhere from thermal camera, what we call color infrared or near infrared, and visible bands. We had LiDAR, hyperspectral, and we also had some cameras with which measures the downwelling radiation, some that doesn't. We used a bunch of platforms. As I said, we had a large UAS, and we also had a number of small UAS. Some of these are belong to my department, and some of them are from the cooperating industries. So I want to talk about a little bit about the amount of data. Agriculture is, or the growing of plant and producing food is a spatial, temporally dynamic process. So, although you have a lot of information, you never know. It's a pretty complicated process, and you never know how plant is doing. And so you know how it is doing, but if you monitor plant and you can get more information, that is more beneficial. So some of the cameras we used are, we used in 2016 are listed here, and what spectral bands and the pixel size and the spatial resolution there. Again, spatial resolution we used a different resolution depending on what our application was and what amount of data it generates there. So a few of the research areas or research problems we were focusing on, one was herbicide drift damage. I estimated the amount of data based on 100 acre. Remember that we are looking at around 102,000 acres. So you have to multiply it with 1,000 if you were to do this for the whole study area. So there is herbicide drift damage, around 6 gigabyte of data. Weed species identification with the thermal image, it is 1.2 gigabyte. 40 gigabyte if you use multispectral data. Plant stand count, 10.5 gigabyte. Yield estimation, 5 gigabyte. Those are, some of the applications we looked at. That is with the small UAS, with our large UAS here. This was our plan to fly twice a month over a 4-month period of time. And also during the first couple of months to generate a terrain model or a digital elevation model. So our estimated amount of data from that project, from that large UAS data alone, was 60 terabyte. In addition to this, there is several set of ground data that we are generating, such as yield data, plant stand count, and any sort of machinery that is going over the field. It's generating all kind of information, what exactly that machinery is doing in the field. So it's we are not used to we are used to dealing with the geospatial data, but not to that degree. So another part of our research was also about educating the stakeholders. Farmers if they are participating, we are collecting this data. They want to use that data for management. So it was difficult to take this information to the courthouse of a small town and show them how to manage, how to download, how to process this data. But we tried. So I just want to quickly come to, I have some research results, but rather than going into, I want to come to what are some of the lessons we learned. First of all, in agriculture, your best laid plans may not work very well. So although we planned all that, we were not able to fly every single time because of weather issues. We generated a lot of data, and that was a challenge for the collaborators. One of the things I want to show is that the collaborator, we planned to collect this data within 24 to 48 hours to stitch it together into a georeferenced image and give it to our collaborating farmer. They can use it with the existing tools to make a decision on how much fertilizer, how they are going to apply fertilizer. So this is a field of a collaborating farmer. I think it is a half section, meaning it is 320 acres. And the Precision Ag software she was using couldn't handle the data, and the original data was 6 centimeter resolution. So immediately we had to go and reduce the resolution to 1 meter so she can handle it. At the same time, we were also working with the company that produced that Precision Ag software. So they were changing the coding so that it can handle big data. So this is a vegetative index generated from the data we provided her. It's 1 meter data, by the way. And this is an application map. There was some conversation about not only generating the data and information, but actually making decision. This is the decision. This map can go directly into a sprayer, and the sprayer can apply fertilizer based on what this map is talking about or saying. Another issue is we have an overwhelming demand for people interested in using unmanned aerial system for precision agriculture, and we don't have the manpower to deal with all that request, both for educational training as well as research collaboration. Again, another lesson learned is that all sensors or platforms are not the same, and the data quality is an issue. And one of the issues, all applications don't require calibration of the data. And if you're looking at the relative patterns, it's okay if the data are not calibrated. But if you are using quantitative analysis, modeling, or things like that, calibration is an important aspect. And most companies we are dealing with are not interested or not doing calibration. And we originally planned that within 24 to 48 hours, we will provide this data to our collaborators so they can take it and make a decision. We are going to replant this field, or we are going to apply fertilizer. In reality, it took, that 4 centimeter resolution data, it took 1 week to process it, just to stitch it together and bring it back to our hand. Again, the company was doing the processing or the stitching together, so we didn't have any control on it. So, these are issues that can be addressed, but these were issues for our project this year. So it was way more time than we anticipated. And again, another issue was data privacy and ownership. Who owns the data? Is it the farmer whose land we are remote sensing, or it's the company that is collecting the data, or it is the university that is doing the research? There has been a lot of concern about that. And out of the 500 plus landowners we had 2 people who really had issues with us owning or us keeping the data. Another issue was export control. Some of the companies brought in software or equipment that was export control technology, and as many other universities, we have a lot of foreign national students and staff. So that was a learning curve and something we had to deal with. How to let our students do their research, still make sure it is safe for everybody to deal with. But based on our work, there is a lot of potential. With this high spatial resolution, you can get information that was not possible with the 30-meter Landsat data or 5-meter rapid eye data. There is a lot of potential, but what is lacking is the analytics, and that is where we are putting our effort in. So I want to show this. The last one is, we are trying something. Oh. It's not working. Anyway, so we are trying something. There was a lot of attempt. There has been a lot of attempt at plant species identification. With even very coarse data, it's not very successful, because when you have a 30-meter or 5-meter data, your plant species all mixed into a mixed pixel, and it's kind of hard to know when you have different soils and moisture level, soil conditions, and terrains. It's kind of hard to say what species were. But now we are collecting data at a millimeter level, maybe 5 millimeter resolution, and you can do 3D analysis. It takes a lot of computing power and the time to do it, but it is possible to do, and that's something we are trying to do. You can look at the morphology of the plant. It is upright, or it is a creeper, or what color it is, or when it is flowering. Now there is something we are trying to do is to identify what are those weeds, where are the invasive species, or the noxious weeds, or the voluntary soybeans in a dry bean field. So a lot more applications are possible. So that's what I have today.
Thank you very much.
All right.
Okay, great. So I'm kind of going to talk about some of the analytics issues in more detail, and but also kind of show the whole life cycle of data. And in terms of my color of glasses, I come from GIS or spatial computing side. And recently, one of the computer science magazines, CSCM, had a survey article on spatial computing based on a workshop that we organized. So these are some of the other things in terms of background. So you can see the color of my glasses. And I think it's a good match with the topic, because sensors usually have to deal with physical spaces. Okay? We already heard about many sensors on the bridges and on the agricultural field. Here are some other ones that many of us have experienced. So I'm showing you a map of a highway network in Twin Cities. And these highways nowadays have thousands of loop detectors in the pavement and cameras through which you can monitor traffic. So you have these fixed sensor networks. But in addition, now as we are hearing about Internet of Things, there are many mobile things, cars, cell phones, which have GPS trajectory. And then finally, even people are adding to the data. So you get many different kinds. Just GPS trajectory gives you a lot of information. And as you can imagine, in your cell phone, if you have not switched off your location services, Google and Apple are sort of keeping track of you for weeks and weeks. And they can see your home and work and many other things just from that lot of information. This is showing you something more. When the GPS is in the car, actually there are onboard diagnostics about the engine, and you get hundreds of other variables. So here we are actually showing you fuel efficiency and with elevation change. And you kind of see this fuel consumption drops dramatically based on elevation and other conditions of the road. Okay? And then social media, many of us think about. So these are a lot of different data sets which are coming around. And as you can tell, many of these have locations. And location-based data is a pretty valuable segment. So in the big data report from McKinsey, they estimated, one of the largest value segment was location-aware data. You kind of see 600 billion, which is more than the revenues of most of the IT companies combined. And it's just from fuel saving, just one application. But there are many others. With Internet of Things, we'll see a whole lot more applications of this kind. So, and as I said, if you look at the trends, these sensors are getting richer. You kind of see many people who can carry, different things. For example, here an asthma inhaler People have added GPS on that, so you can actually track when it is used and correlate it with environment and conditions. Volunteers are doing air quality monitoring, and through that you can make maps of cities to see the air quality conditions based on that. And even going further, things like tweets, which most of us think of it as text, but about 2 to 5% of tweets have locations. So using that, American Red Cross actually makes a map to monitor disaster-related tweets, and that gives them a head up about an hour, 2 hours ahead of TV news about disasters, and they can send relief. So these have come to common practice, but there are others which are primarily in Department of Defense today, but you are going to see civilian usage very soon. So if you think about wide area motion imagery, so on the larger UAVs, you can put 100 cameras together. So a single image, you can cover almost 100 square kilometer at a pretty great resolution. And you can take an image almost every second or minute and really do a very detailed monitoring of dynamic events. Okay. So the sensor technology is kind of pretty rich. Now you have to kind of think about the second topic, big data. And this is the main point of the whole talk. The big data tools most of us come across, whether they are from machine learning or Hadoop, what you read in New York Times and great media about, they were actually designed for a very different world. Okay, most of these were designed by companies like Google, Facebook, and Microsoft, and their main interest is something very different. They make money out of advertisement on your cell phone or on your web page. So they were mostly designed to mine your click stream to show advertisement. And in this world, there are interesting assumptions which are not true in sensor world. One of which is that the cost of false positive is negligible. If they show you a wrong ad or irrelevant ad, they lose maybe a millionth of a cent. That's about it, right? But that's not the case with most of the sensor we heard about. If you're monitoring a bridge and you give a false positive, that's going to disrupt life, right? If you're monitoring agriculture. So for sensor data, a lot of these generic tools don't really fit very well. And a simple way to think about it is the cost of false positive. But you can actually go in more detail. These data sets are embedded in low dimensional physical spaces and so on. Also, there is a trade-off between prediction error and the model bias. Machine learning goes one way, but in the physical space, we may want to go the other way and so on. So I'm going to illustrate these differences through different stages of life cycle of data. So let's start with the capture. We just heard about the agriculture case. Once you take an image from a UAV, very first thing you might want to do is geo-registration. And that's, takes time. How do you match it with location and so on? And here again, you need to know a little bit more than just saying, here are 2 data sets, I'm going to overlay them. So let me show you one challenge through a story that played out in the media. So when you have geographic data, actually there are many different coordinate systems, and you have to be careful which coordinate system your data comes in. Particularly when you have 2 data sets, the coordinate system must be matched or translated properly. So here is a story. So North Korea, in mid-90s had yet another missile with bigger range, and a popular magazine economist wanted to show the range of that missile. So they took a common map, which is shown here. They put a center at North Korea and they drew a circle with the range of that. Okay, and according to this map, mainland US is not threatened. So what's wrong with this map? What's wrong with this reasoning? Right. So if you're going long distance, tens of thousands of kilometers, you have to take into account spherical shape of the Earth. Otherwise, you have a lot of errors, right? So the actual one, if you drew properly, it will look like this. So this is for a larger scale data, but even in a smaller scale, if you're looking at GPS and you're looking at Google Earth, they don't use the same coordinate system. You have to be aware of those two and translate properly. There are hundreds of these coordinate systems, and this is one of the issues you need to think about as you're in physical space. Let's maybe go to the next step. Let's say we did register the data. We now want to put it with a proper schema, maybe in a database. Then it again turns out the generic databases, what you get with key value pair or on simple SQL, they don't model spatial parts very well. So you have to look at specialized products. And many of you, I assume, are using things like PostgreSQL or Oracle Spatial and so on. Now, the same reasoning actually goes forward with big data tools. When you're thinking about Hadoop and so on, you have to again rethink. So in Postgres and PostGIS, you have spatial libraries with points, lines, polygons. You have proper data structures like R trees. But in the Hadoop world, when you're thinking about data partitioning, this issue revisits. a basic MapReduce essentially goes and divides the data at random. So the nearby things are all over different processor. And that leads to very poor performance for spatial data sets. So even in the big data environment, you have to look at better tools. Like, for example, one from University of Minnesota called Spatial Hadoop, or ESRI has its own tool, where the data partitioning tries to preserve spatial proximity to get you better performance. So moving forward, when we go to analytics, again, you have to be careful about these issues. So here I am showing you a basic stack in Apache Spark, or you can look at the older stacks on MapReduce with the, Hadoop and Mahout, and they have basic machine learning libraries. But a lot of the assumptions made in machine learning don't make sense for spatial data. So let me illustrate with a very simple example with clustering, where many of us probably know k-means algorithm. How many of us know? Quite a few. And k-means does have some sense of space because it uses distances. But let's see, if I give k-means 3 sets of points, one is here, and one is here. If you feed it to k-means, it will always partition and give you some clusters, right? So it partitions and does that. But are those clusters really meaningful? Because many of us, when we talk about clusters, we are looking for natural groups. Are these really natural groups or not? If you took a spatial perspective, you would view this very, very differently. And this is how a spatial one would say. Okay? First, it will say that this data set is complete spatial randomness. So any partition you impose here is really a chance partitioning. If I had another incarnation of that, you don't have a lot of confidence. False positive risks are very high. Okay? And this data set is actually what we call D-cluster. These points don't like each other. Don't try to group them. Okay? They are solitary points. But only over here you have a positive spatial autocorrelation or clustering, and some clustering of this kind may be statistically interesting. Okay? So in spatial world, tools are different, and some of those are actually ported on ESRI GIS tools for Hadoop. And I hope some of those will come to Spark as well. To give you a more specific example, National Cancer Institute, when they look for cancer clusters, they use their own specialized tool called SAT-SCAN, which was custom developed for them. And in this world, they are very worried about chance events and false positives. So they test for that. So for example, this is an old map of London cholera, 1854. How many of us have seen this before? Okay, not a few of us. Okay, good. In public health, it's a very famous map. This is where a lot of public health ideas start. So John Snow actually had plotted cholera deaths in London, and he noticed that they were spatially clustered, and center of that is a water pump. And then, this is where germ theory was born 20 years later, and so on. Of course, John Snow did not have spatial statistics, but if you use these tools today, it will give you a nice circle, and it will also give you some statistical confidence with likelihood ratio and p-value to reduce the chances of false positive. Okay? So these are the kinds of tools, because we are so worried about false positive, we actually go to extra step to do a statistical test, and people might do further tests beyond that. Okay? So in this world, you have to deal with issues like autocorrelation, heterogeneity, edge effects, and you have different theories, like, and you can see spatial statistics, spatiotemporal statistics. By the way, a lot of this was actually started with agriculture census in 1930, when they noticed that the basic sampling theory doesn't account for these kinds of properties. Okay? And this work is continuing, so let me quickly show you one from our group. So here we are showing you Lisner disease in Manhattan. So these little dots are where people were sick, and Lisner disease is known to be caused by water sources like sprays, mists, or water towers. So these squares are showing you some of the candidates that people were worried about. So looking at this map, you can first intuitively ask yourself, which particular water tower will you start testing first? So in the red square, which one would you test first, knowing the spatial distribution of the disease like this? Opera House, okay, that's very intuitive, most of us get it. Now, if you try to run k-means and so on, you can kind of see Opera House may not be center of the cluster. You may get something here, something here, something here, and so on. And in this case, even SAT-SCAN-like techniques, get into a little bit of challenge. So SAT-SCAN gives you these clusters. These two are more significant. Third one is not. And notice that Opera House is in between the two, but it's not in either one. Okay? So we have some new techniques now, finding significant rings. And these are actually useful when you have a source which may be a tower or a chimney, and it doesn't have any immediate things next to it. So there is a hole in your hotspot, and this is what the ring shape kind of detects, and you can see statistical significance. And this is helpful for finding newer patterns. So again, there is a lot of creativity and so on. These problems have richer semantics than what machine learning works with, and better techniques are around. All right, so let's go to the last phase. After the data mining and so on, people often want to just look at the results and explore them for visual analytics and finding more patterns by manual aspects. And again, in sensor world, since we are in the physical world, you can use maps, you can use virtual globes, and many of us have seen Google Earth and so on. In this world, a new trend is to add the temporal visualization. So you're seeing the Google time lapse, where you have taken about a 30-year history, one snapshot per year, and a lot of changes pop out very quickly. So this is the part of Dubai. You can see these constructions pop out. There are similar dashboards. In the space of agriculture, there is a global agricultural monitoring agreement with all the remote sensing and machine learning, and every couple of weeks you get a map like this. And areas where you see crops stressed, the governments can start taking steps very, very early. And many large companies as well as governments are signatory to this. This is another example. Here you're looking at spatiotemporal part. You can essentially look at the sea surface temperature. You can also look at the surface water and issue alerts of this kind. And this is another power of the geographic visualization and exploration of the data. So with this, let me try to wrap up. The main message that I wanted to convey was, if you are working with sensors in physical world, it has some very interesting properties. Your societal applications, have very high cost of false positive, plus the data is in a geographical space. There, many assumptions of the traditional machine learning don't work well. Okay, it's not just about prediction error. You need to worry about bias. You need to worry about statistical significance, autocorrelation, and so on. So better techniques are around. Lastly, I did want to bring up one other issue which is related to that. So NSF is actually now looking at this issue of principles of data science, because there are a lot of applications, but in the foundations also we need to do more work. Otherwise, if we just took tools developed for click streaming in Silicon Valley, apply those to sensors and agriculture, there are lots of risks, and some of that has happened before. How many of you have heard about Google Flu trends before? Few of us, okay. And that was one of those issues where for a few years their predictions worked well, and then there was a huge departure. So this is another opportunity for Midwest, where we actually work with a lot more physical data, not as much click streams, to come together and take a leadership and develop principles. Great. And then the last slide are a couple of papers on this topic, and with this I'll wrap up. Thank you.
We have time for some questions and some discussion. So let me open it up. Does anybody have questions for any of our panelists?
I got it. So I saw a lot of innovative uses of sensors. Can the panel reflect on how your supporting agencies or your funding partners are actually trying to incorporate that rich data into their business processes, their decision making? How hard is that transition, from raw sensing to actual decision making?
Okay, so I guess I'll start with that, since I've been trying to push the technology out with the startup. So it's a tough process in this case, because there's a lot of political agency involved. In case of the infrastructure, there are laws that govern the visual inspections, for example, but they do not incorporate the new technologies in sensing in terms of requirements. And inspecting a bridge can cost anywhere from $10,000 to millions, depending on the type of bridge and type of structure. So the question then becomes, when do they start to incorporate new technology? So it isn't the funding agencies. I mean, the funding agencies like NSF are interested in basic research, and they have funded the basic research. It's at this point more a question of getting the governmental agencies and also the private sector, in case of the railroads, which are privately owned in this country. So that transition is a tough. Well, the railroads have a different incentive structure, because a single bridge out means maybe 50 kilometers, 100 kilometers of track is useless until it's fixed. So there's a kind of a economic incentive. The cities and metro systems and states and so on have an incentive, but they're also more bureaucratic. So they weigh things more politically as well, because it's like something happens, why didn't you do something about it? And whereas if we follow the protocol, then we are following the protocol. So there are liability issues and other kind of sort of information gap, and the economics of that is there, but it's more complicated picture. So I think eventually it'll come, but that may be a slower transition. And cities that are trying to be smart and trying to innovate further, I think will be ones that will adopt technologies sooner. So I'm hopeful that cities that have taken up the idea of smart cities will want to go further.
Go ahead, Shashi.
Okay, I'll talk about the agriculture sector. I go to meetings with the farmers and agriculture consultants, and in the meetings that I have gone to in the last couple of years, roughly 1/3 of the farmers say that they have an unmanned aerial system and they are trying out something with unmanned aerial system. So there is a great degree of eagerness to adopt a new technology. But talking about agriculture in general, any machinery you take today, it has all kinds of sensors incorporated in that. Today if you want, there is a sensor you can mount on the front end of the sprayer, and it will control the application rate of nitrogen fertilizer on the back end based on real-time sensing. We are trying to do some of the same things with the unmanned aerial system. And there are also, at least in our area, we call it the Red River Valley area, the Minnesota, North Dakota border, a number of startup companies that are trying to use unmanned aerial system and different kinds of sensor data to come up with applications in agriculture and sell it to the farmers. My concern as a researcher is that, I talked about the data quality, sensor quality issues with the uncalibrated data. So many a times there is not good validation to say that what they are doing, that this will do, is actually right. So that's, as a scientist, we are trying to bridge that gap and say if some company come up with something and a farmer or a consultant come to the university for verification, is this unmanned aerial system I should buy, or is this a sensor I should buy, is this the precision agriculture software I should be using? It fall upon us to validate it and provide unbiased information. So I think there is, if we can show economic value, even before that, there is a great amount of interest among farmers and consultants and agriculture people in general in adopting these technologies.
Okay. So many examples I was giving, they were all actually in practice. The latest one was GeoGlam. Remember the global picture I was showing for crop monitoring? And in some sense it was driven by the 2008 crisis when food prices went up in US, but many countries had food riots. So they had been actually working on this global Earth observation systems agreement, but that really catalyzed it, and all the EMIS countries signed an agreement. But of course, in order to do that, you have to look at the reality of the situation. In machine learning, we often assume a single machine learning algorithm will work everywhere in the world, right, like mathematics. But that's not true with geographic data. There is great heterogeneity. So many countries have their own satellites, their own sensors, their own machine learning algorithms customized to that. It's an extremely federated system. But at the government, country level, a lot of times things are driven by these crises or the societal needs, and that has happened. The early one I was showing you, highway loop detectors and sensors. I mean, those have been in practice for a while. 1984, Seattle and Minneapolis were the first two cities to try that. And once it was proven, then early 90s, 40 other cities followed. So I think, they have to show the value, and, it has to be a societal priorities, and then things follow through. Yeah.
Just one quick comment on things. There are also sort of externalities and costs that are associated with not adopting the technologies. So for example, in case of nitrogen, it's also one of the most potent polluters, far greater than carbon dioxide by volume. I think 297-fold or something, more potent. So it's a very potent greenhouse gas that's not talked about for, again, political reasons, but there are sort of these other costs where if they're accounted for, then the new technologies would be adopted a lot faster.
In terms of the British application, it seemed like you were talking about a large number of sensors. So I guess one of the questions I would ask is there a major effort to try to optimize and reduce the numbers so that you can get the needed information with less cost?
Well, so the cost lowering is done by lowering the cost of the sensors. So when you had these expensive sensors costing tens of thousands of dollars, you could maybe afford a dozen of them or something if you're willing to invest a few million. By getting the cost down to $200 a channel, what we're able to do is to monitor every single element. And by monitoring every single element, you can then, because all damage is local, it's not just global. And by the time it's reflected in the entire structure, it's late for maintenance. I mean, then you really need major reconstruction. So what we'd like to do is move towards smart structures. In fact, eventually I see, not in the immediate future, but for example, buildings, virtually every floor, every building should have some smart sensors, and especially high rises. And not only that, we can connect this to actuation where you dampen the vibrations. And that can be done with MR dampers, for example, that within a few milliseconds you can, with very little energy, dampen the vibration, because most of the damage is caused by the vibrations building up. So eventually I see not only the sensing to make the structure smart, but smart enough to resist damage. So that would be the next generation of structures.
So most examples that I've seen of sensor systems are single source complete systems where one can expect some kind of uniformity and therefore manageability. Could any of you comment on situations where you have multiple incompatible sensor networks and trying to figure out some kind of joint information?
Yes, actually we've had to do that because, for example, if you're looking at the vibration response, you have to take information into account for humidity and temperature and sunlight. So you have different types of sensors, and that data has to be fed into the model. And so the model has to be modular and distributed in that sense also. So not just distributed, so the physical distribution, but also modular in the sense of taking into account different types of data and so on. And that's where the use of the actor model comes in handy.
Actually, agriculture is a good example where you have a different scale of data, different format of data. Although I talked about just unmanned aerial system, primarily image data, some of the thing there, the LiDAR data is a point cloud. Image data, it could be coming in different formats, but it's a raster data. But we cannot make a decision without, additional information. Soil fertility, soil textural class, yield data, they are all come in different format, especially so for example, yield data, depending on which company's combine harvester you are using, even though it is yield data, each company may have their own type of data that is coming out. So not only the format of the data, but they also come at different spatial scales. Some are point data, some are polygon data, some are raster data, how you combine all that and combine. Some are at every 1 centimeter resolution, some are, many meters or, very coarse data. So that is a problem that agriculture deal with, and you cannot make a decisions just with one type of data.
So I will add, that you have raised the third V, the variety challenge with big data. In some domain, they have, at least for a given purpose, they have tried to pull things together. So GeoGlam is another example where many different countries have their own satellites and sensors, but at least they agreed on the purpose that they are trying to forecast yield. So even their machine learning algorithms are different, but at the output level, they are able to calibrate and link it. But broadly, there has to be more efforts. There were efforts like sensor markup language to do, a little bit more metadata embedding and exchange. Same way within geospatial world, there have been effort to standardize with OGC simple feature types. But yeah, diversity is a great problem. And if we wanted to pull together sensor networks of very, very disparate kind, it will be a challenging issue in general. Great.
So I think with that, we're out of time. I appreciate the education that we've got from our three expert panelists. So thank you very much.
Break now. I think it's time for a quick break. And I just want to add a note of thanks also to Shashi, Dr. Shekhar, who filled in on very short notice. We had a panelist need to drop out this morning, and so we thank him for stepping in. Okay, we'll see you soon. Thank you.